We now go into the details of the first means of communication, namely using shared variables. It is useful to study a concrete example, and here we consider the mutual exclusion algorithm called the bakery algorithm. Its purpose is to ensure that only one of the parallel processes is in its critical region at the same time. On the left, we show a parallel program with two processes. Both perform an infinite iteration as given by the guard true. They then update their own variable to be one higher than that of the other. This means that a value of one's variable indicates one's place in the queue, with a 0 meaning that one does not even want to enter. So the first process enters only once the other process does not want to enter or its own number in the queue is smaller than that of the other one. Having left the queue, it resets its counter to 0, indicating that it no longer wants to enter. Each of the processes give rise to a program graph, produced in much the same ways as we've seen before. As just illustrated, we generate one program graph for each of the parallel processes. Turning to the configurations, we will have one shared memory containing the variables for all the processes, and one node from each of the program graphs, indicating how far the execution has progressed. An execution step relates a start configuration with n nodes and one memory to an end configuration with n nodes and one memory. We label the execution step with the action performed. The end memory is a result of performing the action on the start memory. You should now use the tool on formalmethods.dk to construct execution sequences for the bakery algorithm. Click on some of the red symbols and explore the different non-deterministic execution sequences. Try to find an execution sequence where the variables x1 and x2 become arbitrarily large. An alternative algorithm for mutual exclusion is that of Peterson's algorithm. Here the Boolean variables b1 indicate whether or not the first process is interested in entering the critical section, and similarly b2 and so on for the other processes. The variable x indicates whose turn it is. You should use the online tool to construct execution sequences for Peterson's algorithm, and you should convince yourself that it works as intended. For a more challenging exercise, you should swap the assignments to b and x in each of the processes, and you should show that the algorithm then does not work. Having done this, you should read the section in the book, doing the try-it outs on the way.